is I'm going to look for a network security problem. So I have in here, let's look at the problems I have. I have a classification model for finding guns and images posted on Facebook. So this was a thing that Facebook was doing 5 years ago, basically a solved problem today and not a solved problem back then. A model to identify suspects in a murder case. See this one, a classification model for movie recommendations. It's a special kind of a machine learning problem, which if time permits, I may cover, but it's more of a special topics at the end of the semester but this was a big thing. There was like the Netflix challenge, actually. So Netflix, I think, offered, this was years ago, $1 million probably to whoever did like the best recommender system, which you can imagine how that's important to them because they want people to just keep watching things on Netflix, right? And so recommend is the same problem as Amazon. Amazon, you go on Amazon, they want to recommend this book and they want you to buy it, right? So they need to know exactly that thing that you didn't know you needed to have, right? And so this requires a special technique, which is very interesting. It's called singular value decomposition. I believe someone won the challenge. Weather monitoring. This one is more of a regression problem, so we'll come back to that one. Classification of cancer with 3D images. This is just 3D images. Sentiment in images. Oh, here it is. Number 7, a classification model to detect attacks in network data. So the classic intrusion detection system, for instance, that is AI based. So let's take a look at this. And actually, the data set I provided to you is consistent with that. So what do we know about network data, right? So we have a switch, a router, let's say. We have a firewall. We have a router. This would be your ISP. So this would represent like the insecure internet, right? So the very everyone's scanning you, attacking you, etc. This over here behind your firewall is going to be like your internal network, right? So your, internal where you have your employees. And then over here you have a DMZ or something like that, demilitarized zone. And what you have here is your web server. Web. Switch. So you need to place an intrusion detection system somewhere in here, right? So you have an intrusion detection system. Maybe the firewall is an appliance that you buy that already has intrusion detection capabilities. Or you just have some kind of a device. So I'm just going to put in I'm going to make up some device here. We're going to call it an IDS with machine learning. Okay, so what you might imagine needs to happen here is, to keep it simple, packets are going through this, and this is tapped into the network somehow, and it's basically then capturing all the packets. Do you guys see that? That's it. So that's the medium here. So so then this system, imagine this IDS, basically a packet comes in, the IDS looks at it, and given the packet, it needs to say attack or, good, benign. Do you understand? That's the two-class problem again. So, all right. So we're starting to, we know our goal, right? Our goal is really to flag packets as being either an attack or being good traffic. We know that the thing that we're going to be looking at is a packet. So that's our medium, right? And so now we need to figure out, okay, how do we go from this to X and Y? Because if you do that, you can load that into any machine learning thing, including Weka, PyTorch, all the advanced techniques. Make sense? Same procedure. All right, so now let's go ahead. Let's add a new one. So we understand all of this. Let's add a page here. And once again, we want to use our familiar X and Y to start answering the questions. And remember, at the end of the day, I want you to give me dimensions. So where do we start? We know that we need to identify certain things. We know the vocabulary, right? What are the classes? What are the samples? What are the features? What are the dimensions? So where do we start? What's a sample? First thing, what was the sample? The packet. One packet or several packets? I don't know, you tell me. You're solving it. So think about it. This actually takes us to an important question. What are you trying to do? So one packet could be sufficient, maybe for like a hacking attack, right? Like a code injection, something like that. But what if you're doing denial of service attack? What do we know about denial of service attacks? It helps to look at to see if you have a whole bunch of packets coming in, right? And so in that case, it might make sense that you need packets collected over a period of time, such as all the packets collected every minute. And then what do? What's the simplest solution? Because they're all basically the same type of TCP packet, you just average them. And then look at the average of all the TCP packets received every minute. And that might provide more information about, say, identifying a denial of service attack. However, you could also choose one packet. You just have to be consistent. And it might be that you start with one packet and then realize I needed to do all the collected packets in 1 minute, and so on. So it's up to you. This is called feature engineering. So this problem will require some feature engineering. Okay. All right. So, and there's lots of like, I can attack this problem in like 4 different ways easily, right? But we're going to start with something simple. So a sample, what do you want to do? The simplest thing, every packet is a sample. Do you guys see that? So let's go with that. So every packet is a sample. So one packet. So every time you collect the packet, it's going to be a sample. So then sample 1, sample 2, all the way to sample n, right? Dot, dot, dot. So, okay. We know that. The classes are easy because we just want to find anomaly, not anomaly, correct? That's it. So what's gonna happen is, you have one packet and it's, 0, a good packet. Another packet, 0, a good packet. Another packet, 0, a good packet. Finally, you get one packet and it's got a 1. That's an anomaly. And then another packet, and that's a good packet. Do you see that? So those are your classes. This is a classification problem. So 0, 0, 0, 1, 0, dot, dot, dot. Every sample needs to have a label. How do you collect this? Can a person label these? So we gotta think about that and answer that. All right. Could we do that? Could we collect that data automatically? Got to think about that. So those are challenges in this type of problem. So what do we know about the dimensions? We know this one for sure. That's a 1, basically. All right. What about n? So let's start thinking about n. How many packets can you collect? Lots, right? Lots of packets. So then you have to think, okay, we're going to do this over a period of time. So how long a period? 3 months? Does that seem reasonable? That you could collect packets over 3 months? It's going to be a lot of packets. How many packets do you think that would be? Let's say the university. Trillion packets? More than that? Okay, now I believe you. So, okay, 1 trillion. That's a lot of packets. So the first problem with that, that's not going to fit in Weka. No way. Weka can, so if you want to run this in Weka, randomly select 100,000 of these and load it in Weka just to quickly prototype and see what's going on. But a trillion will not fit in Weka. I would not even recommend that you do this with like a powerful algorithm. So definitely scale down a little. Let's scale down to now 1 billion is doable, but it's a lot. So that's where the whole batching thing that I was talking about comes in. You're not going to give 1 billion packets to the model at once. You're going to give it 64, and it's going to look at them and learn. Then you give it another 64, and it's going to look at them and learn. And that's how the models are built today, which is really excellent because they're built like that. Do you guys understand? Okay, so 1 billion. So you have to think about that. So 1 billion means a lot of resources that you may not have. Okay, so then maybe because you're starting, you say, okay, the next time I do this, the next 3 months, we'll scale it up. But right now, 1 million. How about that? That's still a lot. But okay, you can, if you took 10% of this, possibly it could fit in Weka, for instance. And then your deep learning algorithm with a GPU might take a few days, but you'll train it. Do you see what I'm saying, guys? So that's one of the constraints usually is the computation, the compute, as they call them, the computational resources that you need to have. All right. So 1 million, we settled on 1 million samples. So it'll take what, 3 months to collect, you think? 1 million packets? 1 million? And you're going to store those in files, maybe not even one file, but multiple files. Okay. What are you storing? Well, we can capture packets with PCAP as PCAP files, right? We know this from Wireshark and such things, right? So you then store your PCAP files. Okay, that's a certain amount of size. So we know how to collect the raw data, right? We have a Wireshark, Scapy, T-Shark, whatever it is, all these tools that are available allow us to collect the PCAP files. How do we, and we're going to collect 1 million. We have the resources. How do we label them? Our goal is to say this is good traffic or bad traffic, anomaly, not anomaly, attack, not attack, right? How do you collect this data? How much of the network traffic in this university do you think is attack traffic? Like what percentage? Inside the network. I don't mean outside, like outside the firewalls, but I just mean like inside the network. How much of it do you think is attack traffic? Not benign traffic. Percentage wise. 10%? That seems high to me, actually. Below 5, even maybe 1%. Do you see the challenge there, right? So first of all, you can get a lot of good traffic. That's everything we do. Email, Google, Facebook, even, all the stuff that we do in the network that is converted into packets going to Brightspace, etc. It's just packets that are goodware. So the majority of this, 99% is good traffic, class 0. But getting that 1%, or the 1% might, let's say 2, so it's just to give it some numbers. So 2% is going to be bad attack traffic, right? So that's not a common thing that happens in this network, actually. Every now and then, maybe it's, the IDS flags something, and then that could be an attack, and you collect that. But essentially, that you don't actually want attack traffic in your network, right? That's bad. So you wouldn't want it there. So how do we collect this? So you could just hope, for 3 months, listen, try really hard. And what might happen is you collect a few samples or nothing, right? So you see the difficulty of this problem. So an alternative to this might be to simulate an environment within a sandbox in this here, and this network, and then intentionally run some attacks, but in a control environment just to generate the data. And then you call it attack traffic. Do you see what I'm saying? Because it's actually really hard to find real attacks unless that's what you do for your business and you go to multiple companies and eventually you've collected a list of attacks that you can use. But for this kind of problem, actually, we may need to do synthetic attacks, which you can do. You guys have used Metasploit, NetWalks, tools like that, right? Kali Linux and all that allows you to do network attacks, which basically generates packets. Because at the end of the day, remember, you're going to be looking at packets, and what you want the machine learning algorithm to learn is what are the characteristics in an attack packet that differentiate it from a normal traffic pattern. Do you see that? That's essentially what it is. So you're going to collect the packets. You easily can collect 98% of the goodware, but the attacks you'll probably have to simulate for this problem. Does that make sense, guys? So these are, again, when you're reasoning these types of problems, these are the things you have to consider. This is a bad situation, by the way. This is, again, I'll repeat, this is called a highly imbalanced data set, and machine learning is not good at this problem. Okay, so that's why we learned those performance metrics that we're going to talk about soon. Yeah. Yeah. Go ahead.
To generate data you need, you have to simulate like two virtual machines attack each other.
Maybe you can physically grab a whole bunch of switches, and I mean it's still going to be network packets. Right, you can do it in the sandbox environment. Sandbox, like controlled environment. So you create your own little local network and simulate attacks.
It's like a thing that work on this kind of stuff. Like I don't know.
It's a challenge, is what I'm saying. Yeah, it's. I mean, how else? Tell me how you can get attacked if you don't simulate the attack. Oh, yeah, so that's another thing, but that's probably your policy, and your company would not let you do something like that. You see, so that's the issue. So they're not going to say go to, what do you call it, the dark web and download a whole bunch of malware. Or no one's going to want you to install a whole bunch of malware on these computers that are doing things. So this is a hard problem, is the point. And that's kind of the idea is, remember, somebody says to you, build a machine learning model for intrusion detection in the network. Okay. So you have to be aware that it's going to very likely lead to a highly imbalanced data set. And that's a problem. You can make it less imbalanced by doing a whole bunch of synthetic attacks, right? And there's a lot of tricks to like balance it. Like, for instance, I could just, do 1,000 attacks that are real, and then I calculate the mean and the standard deviation, and then use those plus some noise to generate new attacks. Do you see what I'm saying? Very, very possible. But is that real, though? That's the question. It's based on the distribution, but the synthetic samples you generated are synthetic at the end of the day, not the real world. And so this is a challenge. Okay, but anyway, let's keep going with it. Okay. So we know that it's going to be imbalanced. We know that. We've established it's 1 million packets, right? We did that. What about the features? What are the features? Yes, sir. Hmm? Yep. Exactly. Yeah. And you're the feature engineer, so you have to figure out how to do this. But the key thing is you have to be consistent. And once again, I will say this for all 1 million packets, let's say column 7 is source port, then that always needs to be source port for every packet, right? It can't change because that's the point that the machine learning algorithm needs to learn, right? That the source port here was always port 80, port 80, port 80 for class 000, and then 22, 22, 22 was always 1. You see that? That's perfect. That's perfection in machine learning because the algorithm says, I learned this pattern. Whenever source port is 22, it's a 1. Whenever it's 80, it's a 0. And that's the trick to machine learning, except that there's going to be other variables that contribute, such as protocol. And what about payload? Think about what the packet is carrying. And of course, we are assuming that the packets are not encrypted. If the packets are encrypted, it's impossible to do this because, as you know, encryption is about randomness. Machine learning is about pattern recognition, right? So, although there's things that you can do, but let's just say that. So it's unencrypted, right? Everyone with me? So you see how the process, at the end of the day, we need to arrive at X and Y. So let's finish this one. So I think we just need to drill down on the features. All right, so we've established 1 million. Let me just say 1 million packets in X. This is X. This is Y, the Y vector. We've established that this is also 1 million. This one was easy because this is 1. We know these are mostly zeros with a few ones. Highly imbalanced data set. We established that a sample is a packet, right? Every packet is a sample. So all we have to define now is F1, F2, all the way to Fm, the features. Definitely the features are coming from the packet. So now we have to study what a packet looks like, right? So do we use UDP packets and TCP packets? Probably not. The reason being that, a TCP packet will have a TCP header, a UDP packet will have a UDP header, different fields. You see that? So you want to, at least in your first pass, you want to be consistent. So just TCP packets, for instance. Okay. So then a packet will have an Ethernet header, right? So now we need to think about where these features are coming from. So Ethernet, followed by what? IP, followed by what header? TCP, and then payload, right? Do you see that? So, we know that Ethernet has how many variables? Let's say like 50, right? We know that IP has how many? Maybe 30 to 40 variables. TCP also has, 40 or so variables. And then the payload is variable length, actually, right? It can have, but it's about 1,024 bytes or something like that. We need to start to drill down and define those. To keep it simple, let's say we're not going to include payload right now. Let's not overcomplicate this because then this almost becomes a language problem. If you think about it, right? So it's going to have words in there, possibly, right? So this is an attack, So we're just going to focus maybe on just TCP and IP, and let's also ignore the Ethernet. So now these are the two headers from which we're going to extract the features. So as you said, what's your name, sorry? James? As you said, source port, destination port, protocol, right? These are the things that we can start looking at as our features. Got it? So you could say Then feature 1, source port. Feature 2, destination port. And then the last one, protocol. But there's more things like number of bytes sent, number of bytes received, right? That gives you information. Those are fine. Now, this then translates into something called the vector space model, which is what I want you guys to understand, right? So I have said that F1 is always the source port. So that means that for sample 1, this packet, we know the source port of it. For sample 2, we know the source port of it, right? That's F1, feature 1, column 1. Then feature 2 is the destination port, and feature M is the protocol. So the vector space model is this very interesting thing. Let's take a look. It's a graphical representation of the columns in the X matrix. So let's take the simple example of just 3 columns. So we have N, we have F1, F2, F3. When you've built this X with this approach, you are effectively creating a vector space. And what a vector space means is a geometrical space, such as this one. So we have 3 columns. Do you see that? A 3D vector space. 3D. So these are basically equivalent to being axes. Every column is equivalent to being an axis in this vector space. Do you guys understand that concept? And they are essentially 90 degrees. They should be. They won't always be, because sometimes they can be correlated. So for instance, if I know that it's winter, I also know that it's probably 32 degrees. If it's summer, it's probably 80 degrees. Those two are correlated. But that doesn't, ignore that. And then just know that when you build your X matrix, you're also building a graphical space, F1, F2, F3. The really nice thing about this is, and this is pure geometry that you learn in high school. So you've done this. But the nice thing about this is now every sample, S1, S2, all the way to Sn, every sample is a point in this vector space. Do you guys understand that? So for instance, I can now, given the values of F1, F2, F3, I can say sample 1 is this point, sample 2 is this point, sample 3 is that point. Do you guys see that? Right? Because, let's say that this is 10, 10, 10, right? So sample 1, give me the coordinates approximately. It would be F1 is like a 7. F2 is like a 4 maybe. And we're going to say that F3 is 0 basically, because they're just like essentially on that plane. You see that? All right. Let me erase this one. All right. Go back to the pencil. S2. S2 is this one over here. Right? So this one characteristic that it has is that it's not on this plane. So it's on the F3 axis at about 5. Do you see that? So this was 0, this is a 5. Makes sense? Even though, and then let's say it projects from like here, just so that we know on X, it would be, what is that, a 3? And this is like a 2. Got it? Let's do the last one. So S3, let's say this is S3. So this would be X here is like a 2. F2 is like 6 maybe. And it's also on that plane. So it doesn't like come out on the other axis. So this is, let's say 1 or 0. Do you guys see that? So that's the magic of this. As you're putting in these samples with columns and rows, where the rows are samples and the columns are features, and you're quantifying them, you're essentially building this vector space model. And now the points have very interesting properties. So for instance, geometrically, I can say things about this. I can say, for instance, I can ask you the following question. Is S3 closer to S1 or to S2? Is S3 closer to S1 or to S2? S1, exactly. So if I build, the distance, it would be like versus this little distance. So, if I ask you, Taylor, right? Taylor. Yeah, Taylor's distance from you, right? What's your name? Jonah. Taylor to Jonah versus what's your name? Jake. So is Jonah closer to Taylor or is Jake closer to Taylor? You are, right? Same thing, 3 dimensions. Make sense? That's the vector space model. Same thing. Now, KNN, which is the algorithm that we're going to look at on Wednesday, is entirely based on this. Now, I'm going to ask you one more thing that's really important. So humans can see in we can see one dimension, which is basically this pencil is one dimension. 2 dimensions is just things that live in this plane, or 3 dimensions, which is literally this space. That's why I did the Taylor and Jonah example, right? But okay, what if I have like the example of the first example we did, right? What were the dimensions of that X? I think we said 1,000, and this was, you gave me the number, 2,352, I think. That's 2,352 features and columns. Do you see that? So what do you think about that space? This space has 3 columns and it has 3 axes. If I had a space, an X that has F1 and F2 has 2 columns, and it would be just a plane like this, X1, Y. So from that, you can infer what? For an X matrix that is 1,000 by 2,352, this would create a vector space of how many axes? 2,352. We can't even, so we can visualize that. We can visualize that. We can visualize that. But if we add a 4th column, there's an additional axis. We can no longer visualize it, but the math of it works the same. So that's the beauty of it, that we can represent our images with 2,352 pixels, but we can still plot them as little points in there and measure distances between them. That's the vector space model. Do you guys understand, guys? Pretty important concept to grasp, as some algorithms in machine learning are entirely based on these geometric ideas. Yes, sir. Yes, 5 planes. And the way that we write it is actually, this is R2. Oops, that looks terrible, but R2 for this one. This one is then what? R3. This one is, because you don't want to draw this thing, right? You're not going to start drawing 2,000 axes. So you simply say R 2,352. We cannot visualize it, but I can definitely build a KNN that will compare the distance between one point and the other, and I'll be able to say something about it, just like we did for this one over here that we can picture. So to answer your question, how many axes did you say? 5 or 5 columns? Yeah. So what he's saying is an X matrix that is like this. So n samples, but there's F1, F2, F3, F4, F5. So that is essentially 1, 2. Notice all of these are 90 degrees from the other, and that would hold mathematically. So 4, 5. But, it's easier just to say 5. But I can definitely say, what is the distance between S1 and S7 versus S1 and S9? And I will get, based on where they fit in this vector space, I'll be able to say something about it. And this is what we will be doing with KNN. We'll use a metric called the Euclidean distance, but there are others as well. Got it, guys? Pretty key concept to understand. The vector space model, sometimes written as VSM, vector space. All right, the last thing I want to say today is so I always make a note. If there was a statistician right now in the room, they would have complained about something that I said. And it's pretty important. Let's go to the example of just 3 dimensions because it's easier to picture. But we're going to stay with network security. So I'm going to say, right, so we have something like this, and we said it was source port, destination port, and protocol. So when we're talking about destination port 22, port 80, right? Port 443. Do you guys see that? So essentially, if we had an X matrix, right, to represent these samples as F1, 2, and let's just focus on F1, which is destination port. Then sample 1 might have a destination port of 22. That's SSH. Sample 2 might have a destination port of port 80. And S3 is 443. Right? That's what I'm saying. So in this axis here, essentially what we're saying is that port 22 would be like there. Port 80 would be like there. And then maybe 443 a little further down. Do you see that? Because they're numbers in this axis that I'm creating. However, there's a problem with this. And the problem is that to machine learning, somehow, it'll look at this and it'll say, so somehow this sample 3 is in this feature is more than this one. And that is not an accurate description. Port 443 is not any greater than port 80. It just means something, but it's not more. For instance, 443 is not more 80ness any more than port 80 is more 22-ish. You know what I mean? So what people would recommend instead of doing this this is easier and it might work, but for math people, a better representation of this would be a categorical representation. So what I mean is, let's say the only ports you had in there were 22, 80, and 443, right? In that feature F1. It turns out that's the only ones you had in there. So then based on that analysis, you would actually say, okay, no, a better representation is to break this down into 3 columns. You see that? So now you would say that this is actually, you would have to like write some code to modify it so that now this column is 22, which essentially it just means, does this contain port 22 or not? It's a more of a categorical thing. Port 80 would become its own column also. And the question there would be, does this packet include port 80 or not? And then finally, you'd have a 443 column. And the question, once again, is that. So in this packet, obviously, so this is S1, and we'll finish with this S2, S3, right? Which is still S1, S2, S3. So essentially this was port 22. So now we one hot encode it by saying, oh, this is 22. So then we would say 22, yes. 80, no, no. Next one, port 80. Is it 22? No. Is it port 80? Yes. Is it 443? No. Last one. You guys tell me. Is it port 22? No. Is it port 80? No. Is it port 443? Yes, one. And that's called one hot encoding. That's a better representation because people will argue, as I said before, there's no meaning in saying that port 80 is greater than port 22. It just means that this is SSH, this is HTTP, but no such meaning actually exists. And you don't want the machine learning algorithm to think that. So by doing it this way, you're preventing that. So you're essentially helping the machine learning algorithm to think about this problem in a better way. Got it? It's harder, I get it, because you have to convert from here to here, but it's a better approach. All right, guys, so we did two problems. I may do maybe another problem on Wednesday of this, but maybe after we finish the KNN algorithm, which shouldn't take that long, but just that'll be our first algorithm to understand. And I've given you some of the foundation with the vector space model, okay? So remember, the key thing is every sample is a point in these vector spaces. All right? All right, so we can stop here for today. So I'll stop the recording here. And I've assigned a homework,